February, March 2023, paper 42. Okay, just go over with you lah. What are the things that came out? Gravitational field near the Earth's surface is almost parallel. And definition for gravitational field strength and gravitational potential. Can review it in your free time lah. Newton's law of gravitation. Point mass distance between the, the point mass is much greater than the size. Right? And satellite motion condition for geostationary orbit. And then usually they will ask you to derive this formula lah, but they modify it slightly lah. Okay. Define gravitational potential at a point. Okay. You can try without looking at the answer. Speak and you can listen to it also. And memorize it again. Can? Hold on for unit mass. In moving the mass from infinity to the point. Okay. Artemis is a spherical planet that may be assumed to be isolated in space. The variation with distance x of the center of Artemis of gravitational potential is shown in figure 21. Right? That is in your formula sheet. Be aware of it. Radius of Artemis is 4,800 kilometers. Determine the value of phi on the surface of Artemis. This is just asking you to read the graph. So you just read this one, 4.8 times 10 to the power 7 meter. Just draw a line or use a ruler and then draw another line there to read. Okay, negative must be there. Show that the mass of Artemis, we know the potential. Use the potential formula. That formula, put in your value. And to find the mass, rewrite the whole thing. Don't worry about negative sign. Just substitute your value, potential, and then this one is that. And this is your G. Unfortunately, the computer keep on changing my what is happening to this program? Keep on changing my 10 to the power 10 to the power 7. Okay. Any comment? Cannot hear you, too soft.
Okay.
This is what we have found. Calculate the gravitational field strength G on the surface of Artemis. Right? That is what we have found. We have used our formula. And G is Gm over R squared. You can substitute in the value to calculate out. But the fastest way would be to use this value of phi And there's an R there. Gm over R is 5 divided by R. Then put in your value of 10 to the power 7. Okay. This is your R. And then you get your answer. Why is this program keep on changing my thing? I just corrected it this afternoon. So me, if you want to ask a question.
Okay.
A satellite is in orbit at a fixed position above the point on the surface of Archimedes. The satellite is located at the equator of Artemis at a height above the surface where the gravitational potential is minus 6.5 times 10 to the power 7 joule per kilogram. Calculate the period in hours of rotation of Archimedes. Well, they have given you this potential, so you use a graph. Use a graph. Right? The potential is here. Then read the height. R we have found from the graph. And this is a way of asking you to derive. To memorize the formula. Basic formula, memorize it, but don't memorize the whole answer. Then cancel the M, cancel the R. Then you get your V square is Gm over R. Then change this to period. Replace V by 2 pi R over T. Okay. So subject T, you get that one there. Put in your value and calculate out. Okay, change it to hours. Okay or not? Anything not clear? Okay, good. State one similarity and one difference between gravitational potential due to a point mass and electric potential due to a point charge. You want to try first?
Gravitational potential is always negative.
Then
For difference,
for difference, yeah. How about
similarity
point charge?
similarity is inversely proportional to distance.
Okay. Inversely proportional distance from point. Any of this one. Points of equal potential lie on concentric sphere, 0 and infinite distance. Difference. Gravitational potential is always negative. Or electric potential can be positive or negative. Okay, good. My ideal gas assumption, make sure you know by heart. For internal energy of ideal gas, right? Make sure you know that. And this is the ideal gas equation. What's an ideal gas? This quite common, come out a few times already. Then what is pressure exerted by the gas? Avogadro's constant is something strange definition, Internal energy of the system, okay. Then make sure you know how to derive the equation. Right? Derive this equation from these two equations. Okay, what is meant by ideal gas? Can all this must be by
Ideal gas,
say again.
rho v proportional to T.
It's 2 mark. So the first mark will be given to gas for which PV is proportional to T. That's the first mark, where T is the thermodynamic temperature.
Oh,
Okay, for all pressure and temperature actually for all pressure and temperature but they don't require that but it's no harm to write it down there in case they change their mind. A fixed amount of helium gas is sealed in a container. The helium gas has a pressure of, so written there right? Temperature, volume, pressure, and the pressure changes, the volume changes, the temperature changes. No thermal energy enters or leaves the helium gas during the process, right? No heat enter or leave the system. Show that the helium gas behave as a ideal gas. How to show? Yep, how to show? You said, definition. PV over T is constant, no?
so you solve both of them, and
Ah,
then
just show them
uh,
PV, P1, V1, T1 for this one. And then P2, V2 for T2 for this one. And show that both of them are the same value. And then they are equal. So therefore, helium behaves as an ideal gas. That's all. The first law of thermodynamics may be expressed as delta U plus Q plus W. Use the first law of thermodynamics to explain why the temperature of helium gas increases. Okay, you want to try?
uh, internal energy increases. So
How do you know that internal energy increases?
because both is done on gas.
Yeah, so Q is 0, right? And then this is work done on the gas. This is the initial volume, so there's a compression involved. So work done on the gas. So there's a rise in internal energy. So if there's a rise in internal energy, there's a rise in temperature. Okay, can
Okay.
the average translational
Yeah.
kinetic energy of the molecule of an ideal gas is given by that. K is Boltzmann's constant, and T is the absolute, T is the thermodynamic temperature. Calculate the change in total kinetic energy of the molecules of helium gas. Just use this one, no? But first you have to calculate the number inside here, no? So you can use either one to calculate. Right? PV equals NKT. Subject your N. Put in your value of PV. No? Can use either one of them. Put in the value. Then calculate out. Then use this one. Right? Common denominator delta T. So 3 over 2 N. N is that one there. There's your N. There's your K. change in temperature 742 minus 27 no? In the diagram. Calculate out. Okay. Right. Is given a formula sheet. Remember that. The mass of nitrogen in a container is 24 grams at temperature of 27 degrees Celsius. The gas is cooled to its boiling point of minus 9603 degrees Celsius. Assuming that the gas condenses to a liquid, from the changes for this change, the specific capacity of nitrogen is given, the latent heat of vaporization of nitrogen is given, determine the thermal energy in kilojoule removed from the nitrogen gas. Okay, calculate one by one. No? First, heat given out when nitrogen condenses to liquid, right, from gas to liquid at the same temperature, change to kilogram because it's given in kilogram also. Here this one. Then right, this one change to joule, calculate out, and heat given out when it cools from this one, that temperature. Okay, M there's a C. You just add the two together, minus minus plus, oh, minus minus become plus. So add the two together, they want it in kilojoule. Right, round it up to three significant figure. Okay or not?
Okay.
Remember the first law of thermodynamics, the definition. Right? This is what we have done. Summarize for you the first law. Right? As a statement. Usually it's worth 2 marks. An object is suspended from a vertical spring as shown in figure 3.1. The object is displaced vertically and then released so that it oscillates, undergoing simple harmonic motion. Right? These are the formulas given in for simple harmonic motion in the formula sheet. Kinetic energy, potential energy, and total energy of the oscillation are each represented in one line, PQR. State the energy that is represented by each of. Okay, what is P? Yeah, what is P?
P is the total energy.
Q?
Potential.
Potential energy? Okay, good. Object has a mass of 130 grams. Determine the period of oscillation. Okay, how do you solve this question?
Half m omega square. X
Okay,
square.
use the total energy formula. Half m omega square x naught square. Because you can read the total energy easily. And subject omega. Put in your value that you read from the graph. Read from the graph there. It's in millijoule. That's why 10 to the power minus 3. Then mass change to kilogram. X naught reading from here. From here. Then calculate get your value. Then your period is 2 pi omega. Okay.
Okay.
What causes damping?
Resistance. Wait.
Resistive force. Motion is opposed by
Resist.
resistive force.
Yeah, resistive force.
A light card is attached to the object. The object is displaced with the same initial amplitude and then release. During each complete oscillation, the total energy of the system decreases 8% of the total energy at the start of the oscillation. Determine the decrease in total energy in millijoule of the system by the end of the first 6 complete oscillation. So energy left after each oscillation is 92% left. Decreased by 8%, so 92% left. So energy left after 6 oscillation is just 0.92 to the power 6 is the initial energy. Okay. Decrease in energy, initial minus final, millijoule. Okay or not?
Yeah.
State with reason the type of damping that the card introduced into the system.
Light damping.
Light damping, because the amplitude of oscillation gradually reduces. Or light damping because the system still oscillates. Okay, state Coulomb's law.
Force directly proportional to product of charges.
Electric force is directly proportional to the product of charges. Force between point charges is inversely proportional to the square of their separation. The charge sphere X, this is your charge sphere X, is supported on an insulated stand. Second sphere Y, that's a Y, is suspended by a thread so that the sphere Y is in equilibrium at the position shown. The charge on the sphere X is given, the sphere Y is given. Assume that the sphere behave as point charges. The length of the thread is 1.2 meter, and the centers of the sphere X and Y are separated by horizontal. Is given center to center. These are, you can use either one, either epsilon or 1 over 4 pi epsilon, which is come to about 9. Okay, there's a formula sheet, there's a data sheet. Alright, this is your AS work. Show your forces acting. The weight is the first one, mg, going downwards. Repulsive force, so there's electric force, and there's a tension. Right? There's a marking scheme. Determine the mass of sphere Y. So either you can resolve in the component or use vector triangle mg plus f plus t. Right? And this angle is theta. Or this is also a triangle. Similar triangle. 1.2, 0.08 meter. So that's the formula that we are using. Put in your 1 over 4 pi epsilon naught. Right? That one is 9. Change to SI unit, 9. The other one is 64. And then distance is that. So we can calculate our F. Calculate our F. And sine theta. Sine theta is this one over there. We can find our theta. And we can use these two tangent. So mg, right? Tangent this angle which we have found equals to F over mg. So mg equals to, right? Just manipulate that's all. And we get the answer. Then divide by g to get our m. Can. Okay.
All right.
Calculate the total potential energy stored between x and y.
Yep.
Right? That's we have calculated the force. Now total energy is just the force times R. Right? Simple simplification. If not, you can work it out. You can use this formula. Using this formula to work it out. So I prefer this F times R. F times R is equal to E. Then put in your F value, put in your R value, and calculate out. Okay. An electron enters a region between two plates P and Q that are separated by a distance of 18 millimeter, as shown in figure. The space between the plate is a vacuum. The potential difference between the plate is 250 volt. Electric field strength will be assumed to be uniform in the region between the plate and zero outside the region. State the direction of the electric force on the electron when between the plate. Okay. Yep. Direction of electric force on the electron.
It's towards plate P.
Say again.
Towards plate P.
Plate B. Okay. How do you decide? How will you decide? Yep. How will you decide? 10 more minutes. How will you decide? Electron is attracted to the positive plate. Lor.
Looking at the
That's how you
yeah.
decide. Lor. Electron is attracted to the positive plate, so the force is outwards. So determine the magnitude of the force acting on the electron in the electric field. We calculate your E first from V and distance D. Okay. Then your F is EQ. That's your capital E. That's your Q, charge of electron. Okay. Explain why electron does not follow a circular path.
Mm,
Yeah.
Because the force is always in the same direction.
Yeah, force is always in the same direction. Perpendicular velocity, right? It's not perpendicular. The force is not always perpendicular velocity that's required for circular motion, but this is not. Or the force is always in the same direction. Either answer. Capacitor, electromotive force, 12 volt, resistor, R, and a two-way switch are connected in the circuit shown in figure 5.1. The switch is initially in position S, where the capacitor is fully charged. The switch is moved to position T so that the capacitor discharges. At time T, after the switch is moved, the charge on the capacitor is Q. Right? Remember, this is given in your formula sheet. You can remember, go ahead. Show that the capacitance of the capacitor is 1.5. How to show that? Yeah, how to show that? Look at time zero. Find the charge at time zero. That's where it is fully charged. Right? It's 2.9. Calculate out. Then C is Q over V. V is 12 volt. That is 12 volt initially. Then substitute inside. Calculate out. Determine the resistance R. Right? Since this is an exponential equation, you have to in terms of charge, so use your formula and take the ln of left hand side, right hand side to get this equation. And this is a gradient. 1 over RC is a gradient. 1 over RC is a gradient. Right? Look at the gradient. 2.9 minus 1.65 divided by 5, 0.25. Then you want to calculate R, cross multiply R and 0.25 and calculate out. Can okay or not?
Okay.
Calculate the energy stored in the capacitor at time t equals 0. Common one, just memorize the formula.
Half QE.
Ah, half CV square, half C will calculate out. V is 12 volt, calculate out. A second identical resistor is now connected to resistor R. Okay, now it's parallel. The switch is in position S. When the capacitor is fully charged, the switch is moved to position T so that the capacitor discharges at time T. At time T after the switch is moved, the charge on the capacitor Q is Q. On figure 5.2, sketch a line to show the variation. Okay, how would the graph look like? How would I expect the graph to look like?
Negative, like a negative gradient.
Besides that, it's a straight line with negative gradient, okay? Besides that, 2 mark, would I expect 2 point, 2 detail. Go to the equation, no?
Yeah,
Gradient
starting
is
from
that,
2.90. It's 0, 2.9.
right? Total resistance, the ampere is half R. So half R means that the gradient is double, right? So look at this part, at 5 there. That height must be half of that height. Okay, that's how they give the 2 mark. Okay or not?
Okay.
A Hall probe is placed in the magnetic field. The Hall voltage is 0. The Hall probe is rotated to a new position in magnetic field. The Hall voltage is now maximum. Explain the observation. Yep.
Uh,
Right? 0 when the plane of the probe is parallel to the magnetic field lines. It's maximum when the plane of the probe is perpendicular to magnetic field lines. So, right? They are given the formula for Hall voltage. And they are given a table for material and N. What state the meaning of N? Yep.
Number density of charge carriers.
Number density of charge carrier. Okay. Explain why Hall probe made from silicon rather than copper. Go back.
Smaller N. So higher VH.
Smaller and higher Hall voltage. That's what we want to measure. The higher the better. Okay. Hall probe gives a reading of 24 millivolt when placed in a uniform magnetic field of flux density 32 millitesla. Hall probe is then placed in a magnetic field of a fixed direction and a varying flux density. The Hall probe is in a fixed position so that the angle between the Hall probe and the magnetic field is the same as when it is when the Hall probe was 24 millivolt. Right? That one. Right? That's the diagram. That's the figure. A coil of 780 turns and a diameter of 3.6 cm is placed in a varying magnetic field. The plane of the coil is perpendicular to the field lines. Calculate the magnitude of the electromotive force introduced into the coil in a time of 0.0